In this lesson, we look at the mem module. This is a tiny module that provides some console commands to read and write memory. And here is the key. You don't have to have a debugger hooked up. Debuggers are great, but I always like to have some tools that I can more easily use anywhere, in labs or maybe even in the field. It's a lot easier getting a console connection than to try to use a debugger, particularly on a live system. The main tools that the console gives you are console commands and logging, but there are times you might want to look at some memory. I've worked on both Linux drivers and embedded systems, and along the way added memory commands like the ones in this module. There was one major use case. Something wasn't working right, and I wanted to look at some hardware registers. I wanted to see if the hardware was set up like I expected, or maybe look at some status bits. Or I wanted to set or clear a bit in a hardware register to see what the effect was. Of course, you can also look at global and static variables with these commands. You would just need to look in the linker map file to get the addresses. There is not much to see as far as the API and implementation. It would be good for you to check out that code, but in this lesson, I'll just do this introduction and then do some examples on the console. One thing about these commands, they really provide no protection against trying to read or write invalid regions of the address space. You have to be careful and know what you're doing. If you try something bad, it will likely cause a hard fault and the system will hang. So here are the actual commands we'll be looking at in just a minute. And of course, the ones that we're going to focus on are the memory read and the memory write command. Okay, so we're in the console here, and let's try some of these mem commands. So first, let's just do a mem help, and that gives us the usage. The first thing I am going to do is read at location 2000 and then 4 zeros. 1, 2, 3, 4. If you remember, this is the start of RAM. I am going to read 8 items, and the default item size is 4 bytes. So let's look at that, and there we get that. Now I'm going to look at the same memory, 2000, 1, 2, 3, 4, but I'm going to look at it in terms of bytes. So 8 times 4, so there's 32 bytes, and we want to look at it with the data size of being 1. And so there you have that. Now, the question I could ask you, sort of an aside, is whether this machine is big Endian or little Endian. And the key is just you can look at these first 4 bytes and compare them to the first 32-bit word. And that would tell you. And the answer is it's little Endian. And the reason you can say it's little Endian is the first byte is 03, and that's the least significant byte of this word. If this were a big Endian machine, when we printed out the bytes, we would see 0003. So now I'm going to write some memory, and in fact, I'm going to write this first word of RAM. Now, I've done this. I know it doesn't cause the system to crash, but it's very dangerous. I don't know what that first word of RAM is being used for, to be honest with you. But let's do it. So 2000, 1, 2, 3, 4. And then if you look at the usage for write, you give the address. Oh, I gave the address. You have to give the data unit size, and then you give the values. And I am just going to give the values 1, 2, 3, 4. So this means write data starting at this address, write bytes. The 1 means bytes, and then these are the 4 byte values. And you're limited to some number of values, but certainly it can do 4. So it took that, the system didn't crash, and now I'm just going to cut and paste this command here, and we can see that we have written those 4 bytes. By the way, if we want to look at it as words, um, we see this, and there are those bytes in a word, given that it's Little Indian. So now I just want to look at some flash. If you remember, flash is at 800, 1, 2, 3, 4. And I'm just going to look at the first two words in flash. If you'll remember, the start of flash has the interrupt vector table. And the very first word in that table is the initial stack pointer. This looks plausible. We know that RAM starts at 2000, and this looks plausible. It's actually valid, but just eyeballing it, it seems like it could be a RAM address. And then the next word is the address of the first instruction where it should start executing, the reset handler. And again, we know that flash is 800 and then 4 values. So this looks like a plausible flash address, and in fact it is. So I did want to show you what happens when you try to read a bad address. And I just picked 8,000, 1, 2, 3, 4, sort of at random, thinking I don't know what's mapped there, but it's very possible nothing is mapped there. So I hit that, and what has happened here is it tried to print that address. It got one character out, and then the system hung. And I'm hitting return here, and nothing is happening. If I look at the blinky LED, it has stopped blinking. The system is hung. And it's probably in that tight loop. If you remember when we looked at the interrupt vector table and so forth, it probably hit an interrupt and then went into a tight loop. Now, if we had a watchdog timer set up on this system, the system would reset itself and start running again. But we don't have any watchdog timer, so it's just stuck. So that's it for the MEM module. Thanks for watching.